I'm going to start by proving a trig identity that's going to come in handy when we're dealing with force vibrations. So let's start by showing that you can write a cosine of theta plus b sine of theta as some amplitude, a, some other constant, times the cosine of theta, but plus a phase. That means that a sine and a cosine sum up to a sinusoidal thing, but it's shifted to the right or left. And when you weight it with a and b here, well, then you're going to have maybe a different amplitude. So we're going to find out what that amplitude is and what that phase phi is in order to make this possible. So I'm going to start with Euler's identity here. Euler's formula, e to the I theta is equal to cosine of theta plus I times sine of theta. And you can see that we can take this here, let's put it in this complex exponential sort of language here. I'm going to say a e to the I theta. The real part of this is a cosine theta. That's exactly that. So I'm just writing this term in terms of complex exponentials. A e to the I theta plus b, turns out if we make this a minus sign, minus bi e to the I theta, negative ib times this thing is just going to be b times sine theta. So we're writing this in terms of complex exponentials as well. Go ahead and verify that, multiply that out, and see that the real part of this is equal to that term. And that must be equal to a e to the I of theta plus phi. Okay. And you can verify that as well. So what I'm going to do now is I'm going to notice that a e to the I theta plus phi, well, that's really the same as, let's not erase, I'll say a e to the I theta, e to the I phi, by the rules of multiplying two exponentials together. So we're going to divide through both sides by e to the I theta, and we're going to get a minus bi is equal to a e to the I phi. All right, so now we need to figure out what is a. Okay, well, let's figure out what the magnitude, let's take the magnitude of both sides. That's actually going to give us a formula for a. The magnitude of both sides. The magnitude of a complex number, a minus bi, well, that is just the square root of a squared plus b squared. What's the magnitude of this right-hand side? Well, it's the magnitude of a, e to the I phi. But that is just the magnitude of a times the magnitude of e to the I phi. All right, well, what's the magnitude of e to the I phi? Well, plugging in phi here, we've got a cosine phi, I sine phi. We're just going to take the square of the two things, cosine squared plus sine squared, take the square root of that, it's going to be 1. This is going to be 1. So just the magnitude of a is equal to the square root of a squared plus b squared. We found what a is here. And now let's figure out what phi is then. All right. So the way that we do that is we can go ahead and substitute in, let's say that this is a cosine of phi plus I sine of phi, or ai sine of phi, I should say. Okay. The real parts have to be equal to one another. So I know that a must be equal to a times cosine of phi, capital A cosine phi. And I knew that the imaginary parts need to be equal to one another, so I need negative b to be equal to ai sine of phi. All right, I can just, divide through the two equations, basically. Oops, get rid of that I there. So I'm going to take this equation and I'm going to divide one side by a cosine phi, and I'm going to divide the other side by a. Okay? So I'm going to divide this by a cosine of phi, and this I'm going to divide by Okay, and that is going to leave me with that. I'm going to flip this over to the left-hand side is equal to negative b over a. And so the arctangent of phi, or of both sides, well, phi is going to be the arctangent of negative b over a. All right. Now we can do a picture, and that actually is going to give us a little bit more insight about what's going on here, what this means. We've just found phi there. We already found what this a is. Let's draw a picture to get some intuition for what's going on here. And this is assuming that you've got some familiarity with visualizing complex numbers, kind of like vectors, and visualizing the complex plane. Okay, so I'm going to assume a little prerequisite knowledge of that. So let's draw this stuff in the complex plane. Okay, this is the real part, and this is the imaginary part. What is the number a cosine of theta? All right, well, that's just a cosine theta plus I sine theta. And what this can be visualized in the complex plane, this is something that looks like that. That's the number with a length of a. It's got an angle with the real axis of theta there. That makes this here a times cosine theta, and the imaginary part is a times sine of theta. That's why we visualize it like that. Okay, I'm going to go ahead and erase that. All right, let's take a look at b sine theta. What does that look like in the complex plane? Or really, I should be looking at a e to the I theta. That's what I meant. A e to the I theta. That's what this vector is there, or that's what that complex number is visualized in the complex plane. What is this number here in the complex plane? How do we visualize that? Well, e to the I theta is going to be a number that's at some angle theta. When we multiply it by I, that's basically like rotating that by 90 degrees. Okay? So we'd end up with something perpendicular to it. Then we take a minus sign, so it actually flips it around a further 180 degrees. And so we end up with something that is in this direction here. It is length b, though. And we're saying that this thing here has to equal that thing there. All right? So that means that the vector sum, or the complex number sum, of these two things, which I can visualize by that, well, this here is a, capital A, e to the I theta plus phi. So this is a e to the I theta, and this is negative b e to the I theta, and this number here is a to the a e to the I theta plus phi. All right. All right. So we figure out that, let's see, let's interpret this. Arctangent of negative b over a, phi. Well, a positive phi, so if we go theta over, okay, plus phi is a rotation like that. So this angle here is minus phi. The angle between the theta and the complex number a e to the I theta plus phi, that angle here is a minus phi. And we're saying that the arctangent of that is negative b over a. The tangent is the sine over the cosine, right? Or let's look at this one. Tan of phi is negative b over a. So let's look here. The tangent of our negative phi is this part, which is b, over that part, which is a. And so phi is negative arctangent. Well, we can just put this over here, negative b over a. That's just a way of visualizing that. So we're seeing this in the complex plane. This picture is showing us the same thing there. It's easy to see here that A, the magnitude, also we didn't do the magnitude before. The magnitude A here must be equal to A squared plus B squared, the square root of that, because of the Pythagorean theorem. Okay, so that's a visual representation of this rule here. We can get similar identities. There's a whole lot of them. So let's go ahead and write this out. I'm going to go ahead and erase a little bit. Let's see. I'm going to go ahead and, actually, let's go ahead and just write this identity off to the side here. We know that if A cosine of theta plus phi is equal to A cosine theta, I'm just copying this, plus B sine theta, well, that means that A must be the square root of A squared plus B squared, and phi is negative, I can put negative arctangent. It works like that. You can take the negative sign out of B over A. But what if I wanted a little bit different identity? What if I wanted this to be a sign here? I'm going to make a variable substitution. I'm going to make the substitution that phi is phi prime minus pi over 2. It's just a phase shift here. So I'm going to substitute in this here. I'm going to change my work. I'm going to go ahead and make this phi prime minus pi over 2. Whenever we subtract pi over 2 from the argument of the cosine function, that gives us a sign, basically. We can get rid of that here. Make this a sign. We've learned that, right? Cosine, or you've learned that at some point, of anything x minus pi over 2, well, that's just equal to sine of x, whatever that was. Likewise, sine of x plus pi over 2 is equal to cosine of x. So look, not much changes when we substitute that in. We're going to have to follow that through, and anywhere we see a phi, we're going to have to substitute in phi plus pi over 2. Or phi prime minus pi over 2. Let's just get to the punchline here, all right? I'm not going to adjust this step. I'm just going to erase it. These steps came from that, so I don't want to go through and change that. But this here, this is just going to become phi prime minus pi over 2. Doesn't matter. Whether it's e to the I phi prime minus pi over 2, the magnitude of that term, this term here, is still going to be 1. We're still going to get the square root of a squared plus b squared. We need to change this side over here. This cosine of phi, well, that's going to become a, what is this? Cosine of phi prime. That's going to change to a sine. And this one here, well, when I take a sine of phi and I turn that into a phi prime minus pi over 2, that's going to be negative cosine of phi prime. So I'm going to make this a minus sign, and that's going to become a cosine of phi prime. Okay? We got to fix all this stuff here. So that becomes, the real parts equate. A must be equal to a times sine of phi prime. And the imaginary part, negative b must be equal to negative a cosine of phi prime. So this becomes a cosine here. And that becomes, both sides become negative, or we can make both positive. We can go ahead and divide through. Let's actually go ahead and write this here. B is equal to a cosine of phi prime. Yeah. All right, let's divide through. So a over b is equal to tangent of phi prime. And that means that phi prime is equal to the tangent -1 arctangent of a over b. Okay, so we've created another trig identity here. We see that if we want to express the sum of a cosine and a sine as a sine function that's phase shifted, then we have a very similar expression. We still have an amplitude a is equal to the square root of a squared plus b squared, and our phase is now just arctangent of a over b. I'm going to go one step further, and I'm going to take a look at what happens if we want theta. Oh, notice, by the way, I've just gone ahead and said, written this as phi instead of phi prime. Just changed the name of the variable back to what we had originally. All right, let's say that we wanted to change this just a little bit, actually. So I'm going to actually erase all this here. Okay, now I'm going to modify this slightly. And what I'm going to do is I'm going to take theta, and I'm going to replace that with theta prime. Make a substitution, theta prime minus phi. And I'm going to get some slightly different identities here. Let's make this a little bit neater. Okay, let's substitute that in the first expression there. All right, so that becomes a cosine of theta prime minus phi plus phi. So we can go ahead and get rid of that. Is equal to a times cosine of theta prime minus phi plus b sine of theta prime minus phi. Well, we didn't really change anything about phi, so if this is true, if this is true as well, it turns out that this here can be another expression, and as long as these things are true, then we're allowed to make this expression. You know, we can basically you can think of it as, okay, I'm going to take theta and make the substitution theta prime minus phi right here, and I do it to this expression, it doesn't change. I do it to this expression, that doesn't change either. So for this, a is equal to the square root of a squared plus b squared, and also phi is negative arctangent of b over a. And likewise, we can take the bottom one and we can make in the same substitution. We get a sine of theta prime is equal to a cosine of theta prime minus phi plus phi. Well, oops. Prime minus phi, there's no plus phi, plus b sine of theta minus phi, or theta prime minus phi. Same things are true. A is equal to the square root of a squared plus b squared, and phi is equal to arctangent of a over b. So a is equal to the square root of a squared plus b squared, and phi is equal to the arctangent of a over b. So here are a bunch of identities that we can use when we're working with force vibrations.